Hi class, Assalamu alaikum. It's me, Dr. Sikandar Ali. I am assistant professor with the Department of IT, University of Haripur. Uh, I'm teaching you software construction and development, and previously we take the lab class, but today this is the first lecture class and theory. So we are taking the first online lecture class. Before this we have taken many lectures, but this one is going 100% online. So let's see what we discuss today. So today we are going to discuss concurrency primitives. uh, in operating system we say concurrent processing, but in programming or in software construction we say multi-threading or concurrent thread processing. So actually in concurrency we have to synchronize multiple threads in order to allow multi-threading. So concurrency primitive is a synchronization primitive, and it is a programming abstraction. It is abstraction because the user of the system are the people who see the output of the program will think that all the threads are running simultaneously, but actually the processor are switching between multiple threads. So it is a programming abstraction provided by a programming language or the operating system. In case of operating system, we will call multi-process or multiprocessing. But in case of programming, we will say multi-threading, because in programming we have to control multiple threads through synchronization. In operating system we have to synchronize multiple processor and multitasking system. So it is the programming abstraction provided by a programming language or the operating system that facilitates concurrency and synchronization. For example, you have a program, some small gaming program, and you have some object which are moving, and you are pressing some keys, and the object are moving with the input provided through some keys. At the same time the music is also running. So in this type of game you must have at least three threads, one to control the input and one to move the object or the marker, and the third one to control the music and to synchronize the music and the input and the move of the object. So there are three well-known concurrency primitives that are semaphore, monitors, and mutex. A semaphore is a signaling mechanism used to coordinate between threads. This is a signal passing mechanism which is used to coordinate between multiple threads, and actually in programming it is a variable. We have to declare a boolean variable, or we have to declare an integer variable for semaphore. But the mutex is actually a mutual exclusive lock. You have studied before in operating system what is lock and how we do locking mechanism. If some process need a shared resources, for example a processor, so they first get a lock on that shared resources. So a mutex is a lock which is owned by a single thread. In case of the shared system or shared memory or shared resources, so the thread must get a lock before it own the resources, or it going to enter into the critical system. So actually mutex is a locking mechanism, and we have to implement by programming, we have to implement it through objects. So you can consider semaphore is a variable while mutex is an object. A monitor is a high-level construct which uses an underlying mutex lock to ensure threads have access to some object. Monitor will use both the object, mutex object, as well as the semaphore variable, and they will have a set of instruction, a set of code or code segments to control safe access to shared resources and multi-threading environment. So a monitor is an abstract data type that represents a set of programmer-defined operations that are executed with mutual exclusion. Actually, that is a set of operations on semaphore and mutex in order to provide it mutual exclusion in order to execute multiple threads with mutual exclusion. A monitor contains the declaration of shared variables and procedure or function that operates on those variables. We have a semaphore variable and we have a shared resources, and we have a semaphore variable in the form of shared variable, and we have some steps or function or code or procedure that operates on those variables. The monitor construct ensures that only one process at a time is active within the monitor. Within the monitor or within the scope of the monitor, only one object will be active in the critical system, in the critical region. A mutex mutual exclusion is a synchronization primitive that grants exclusive access to a shared resources by only one process or thread at a time. It is a mechanism, or it is a set of steps or instruction which ensure that the only one thread or one process have access to a shared resources. In order to control access to shared resources, we use some mechanism or some block of code, and the name of that mechanism of block of code is monitor, and it operates or uses both semaphore and mutex uh, mutex as an input. They operates on these object as these mutex object and these semaphore variable. This is a typical example which show concurrency primitive in the form of semaphore. Uh, we have shared resources and we have a semaphore variable in the form of 0, 1, 2, 3, 4 and 5. And here we have multiple threads. So in the diagram it's shown 4 threads, and suppose some processes are requiring some a semaphore and some are releasing. So some require the shared resources. They will update the semaphore variable, the status of the variable, and if some thread release the shared resources, so they will also update the status of the semaphore variable, the value of the semaphore variable. And sometime the process release the shared resource forcefully through a interrupt service routine, and they release the semaphore. For example, some threads are running and have access to, they own the shared resources, and they change the value of the semaphore. But some high priority process or thread come and they send the interrupt service routine send back the current running thread or process to the blocking state and give the resources to the high priority process. So this is a very typical example of semaphore. Now we are going to discuss semaphore in detail. Semaphores are used to manage and protect access to shared resources. In computer science, a semaphore is a variable or abstract data type. It can be a variable or a abstract data type, but in the implementation example we will see usually we declare a boolean variable or an integer variable for a semaphore. So it can be a variable or it's a data type that used to control access to a common resources by multiple processes in a concurrent system such as multitasking operating system. In multi-threading system or in multitasking system, we implement semaphore by a variable, a boolean or an integer variable or an abstract data type. Abstract data type is not the primitive data type, it is the derived data type, and usually we implement abstract data type through class. So object is actually the type of a variable of type class, so we can say object is abstract data type. A semaphore is a signaling mechanism, and a thread that is waiting on a semaphore can be signaled by any. If some thread release the shared resources, so they will get signal, they will update the old value of the semaphore, and the thread which is waiting to acquire the resources will get signal, and then they can get the resources. So it is a signal. If some process receive some thread or some process release the resource, so they pass signal to the other to come and enter in the critical region. It uses two atomic operation. Both cannot happen at a time. So sometime they they will use the operation, or you will implement this by a function. So they will use wait operation, and two, it will use the signal operation for synchronization. They have two purposes. If no resource is available and some thread or process want to take control of the shared resources, they will pass the wait signal to wait in the waiting queue or in the block state. And they pass signal for synchronization. They also have the duty to synchronize between multiple threads. There are two types of semaphore. From the implementation point of view, we have two types of semaphore. One is counting semaphore and the other is binary semaphore. Counting semaphore can have multiple states, multiple value at counting. So we take some example. For example, we have Core i7 system, so there the count limit of the semaphore should be, the maximum value should be 8, and if we implement by binary semaphore, so it should be considered a single processor system, so the value can be 0 or 1, available or not available. Let's see some more details. uh, we want to discuss a counting semaphore first. This type of semaphore use a count that help tasks to be acquired or released numerous times. One task can release one shared variable can be acquired or released many times. If the initial count is 0, the counting semaphore should be created and the unavailable state, no resource is available. And if the count is greater than 0, whether it is 1, 2, 3, 4 or 5, it depends on the maximum limit of the shared resources. If we have a core i7 system, so we can have the maximum limit 8, so it can reach up to 8. The semaphore is created in the available state, and the number of tokens it has equal to its count, the maximum limit. So if the initial count is 0, or if the count is 0, so the semaphore will be in the unavailable state, and the other process has to go in the waiting state. And if its value reaches some positive value greater than 0 and below the maximum limit, so the semaphore will be created in the available state. Let's see some example with two states. We have two states, unavailable and available. For example, if the initial count equal to 0, so the state will be unavailable. If we are in the unavailable state and some thread or process release the resources, so the count will be increased by 1 and it will become from 0 to, it will 0 plus 1, so it will become 1, and the semaphore will change state from unavailable to available. And now in the available state, if another thread or process release the shared resources, so we will also increase the count by 1. So the count will become, the old count is 1 and the new count will become 1 plus 1 equal to 2. But we will not change the state because it's still in the maximum limit. Now if as long as the initial count or the initial count greater than 0, so it will be in the available state. If we start from here, the initial count is greater than 0, so the semaphore will be in the available state. Or if we have some count greater than 0, so the state will be repeated, it will be available. Now for example, we acquire, and when we acquire the resource, so it will change the counting semaphore value, it will decrease by 1. So we acquire another resources, so it will decrease by 1, and again, and suppose the semaphore value reach to 0, the count reach to 0, so whenever they reach to 0, they will change the state and the state will become unavailable. So whenever they reach to 0, it will change the state from available to unavailable. So in summary, if the counting semaphore value is 0, so the state will be unavailable, and if they have any value greater than 0, so the state will be available. Now we are going to discuss the binary semaphore. The binary semaphore are quite similar to the counting semaphore, but their value is restricted to 0 and 1 only. In this type of semaphore, the wait operation works only if the semaphore equal to 0, then the thread have to wait, and the signal operation succeeded when the semaphore value become 1, so it will pass the signal. It is easy to implement in counting semaphore. Let's see some example. If the initial state equal to 0, so the semaphore will be an unavailable state, and in some release the resource, so it will increase the count by 1 and it will change the state to available. Or whether we start from here, the initial count equal to 1, so the semaphore will be created in the available state. So if they release some uh, here, it should be acquire. So if they acquire some, so it will change the state and the state will become unavailable. It should be acquired here. So it have two state. If they have the value 0, it will be unavailable. If it become 1, so it will be available. This is the implementation, and this is part of your practice. But here you just see that a semaphore is a variable, and we call this this variable to we call the semaphore variable through this operator. This operator will return the value related to the super or the parent class. So here in this example, we have two thread and we have method acquire and release, and we have some sleep time. We send back some thread forcefully without completing. We send to the blocking state for after some time. So let's see. Whenever we want to acquire the resource, we will call acquire function, and whenever we want to release the resources, so we will call the release function. And here the maximum count is less than 5, so it means we have a core I5 system. Means as example, you consider that you have only the maximum limit is 5. So let's see the out. We call, we create a variable, and through this variable empty1 is an object and empty2 is an object, and we call the function the method start, and then the other variable we also called start, and then we called with the first variable the join method, and then with the second we also called the join method. So let's see. First it will show us starting A, then starting B. This we give as a message, and then A is waiting for permission, B is waiting for permission, A gets, and then it run 5 times, and then it release the permit, and the B it run start, and the B run, and then B release the permit. Now we are going to discuss simulator and concurrent programming, also known as parallel programming. A monitor is a synchronization construct or a set of operations that allow thread to have both mutual exclusion and the ability to wait for a certain condition to become false. This is a very typical example. If we have multiple processes, P1 get a shared resources keyboard, and they are waiting for some other resources which is occupied by another process. So in order to make P1 capable, that they hold some resources, they have lock on some resources, and at the same time they can wait, they have the ability to wait for some other resources. So a situation can arises if we have process P1 and P2. P1 waiting a resource which is occupied by P2, and P2 waiting for a resource which is occupied by P1. So this situation create a deadlock situation. So concurrency primitive monitor will ensure that some processes or threads have mutual exclusion, a lock on one shared resources, and they can have the ability to successfully wait for another shared resources which is owned by some other thread or process. The Java language and runtime systems support thread synchronization through the use of monitor. In Java, we will use monitor in order to synchronize multiple threads. This is a block diagram of Selenium. We have three states of the threads are the process entry, entry state, and then in the owner state we have two states, waiting and active. So a process can be in the entry state, they enter into the system, multiple processes enter into the system. Whenever you click on something on your desktop, it is the job. First it is the job, and it go to the entry set. Whenever they get a processor, so it become the owner of the processor, and the status of the job change to process. And some process can release some resources, or maybe through some interrupt service routine they forcefully go to the waiting set. So the process can be in the entry set, can be in the owner. The owner have to state they and the owner, and can be in the waiting set. So they can be in the entry, and then when they enter they can be in the waiting, or they can be in the running. If it is in the running, so they will be in the owner seat, and if it is in the blocking, not running in the processor, so it will be in the waiting state. So they can release resources and they can acquire the resource. If they acquire, the state will change from wait to running execution, and they can be completed and they can exit as well. So they release the resources and they exit from the system. This is one of the concurrency primitives monitor implementation. They use the boolean variable in order to show the implementation of the monitor. So if the state available is false, so they have to wait, and if the interrupt service routine forcefully send them to the waiting state, so the available state, if the initial value of the variable is available, still they will become false and will notify all the process. So this is a very typical implementation, and we have used the catch statement because the interrupt service routine if send some process to the blocking state or some thread, so it will throw some exception. So here, so we catch the exception. So this is the example. The last concurrency primitive is mutex. Mutex is a mutually exclusive object that synchronizes access to a resource, usually a shared resource. It is created with a unique name at the start of a program. A mutex is an object, and whenever you write a multi-threading program and you write a monitor code, so you created a mutex with a unique name. The mutex is a locking mechanism that makes sure only one thread can acquire the mutex at a time and enter the critical system. Only one thread can have the ownership of the shared resources, and only one thread can be in the critical section at a time. So semaphore allow multiple threads to be simultaneous, but mutex cannot allow multiple threads should be simultaneously in the critical section. So mutex is an object. In that object, when some process acquire, some thread acquire, so it will change the state of the mutex, and whenever they release some shared resources, so they will also update the state of the variable. So actually mutex providing a lock to some thread on shared resources. It provide a lock when some process wants to acquire a shared resource, or some thread wants to acquire a shared resources, and they unlock the mutex for some thread whenever they are releasing the shared resources. And we have a situation if the mutex is locked by some thread, so the other have to wait, and if some threads want to release the shared resources, so they will synchronize, they will pass the signal, they will remove the lock, and the other process will be notified by a semaphore. So this is some typical example. Some process can send to waiting state, some process acquire, and we have to change the state of the mutex when some shared resources is acquired by some thread release the shared resources, some thread go to the blocking state. So in all the situation we have to update the state of the mute object. So mutex is object on shared resources, and they give exclusive lock to some thread whenever they get the ownership of shared resources, and whenever they want to release, so the mutex state will be updated and they will release the lock for the thread. At the last point of the lecture, at the last slide, we want to differentiate between semaphore and mutex. So we will discuss these two on different parameters. The first parameter is mechanism. So semaphore mechanism is a signaling mechanism while mutex is a locking mechanism. Data type semaphore is an integer variable. It can be integer in case of counting semaphore, and it can be boolean in case of binary semaphore. Mutex is a object. We have to declare object is a type of class, and it can be a type of boolean and a type or can be a type of integer. Modification: the wait and signal operation can modify a semaphore. The waiting operation and the passing signal operation can modify the state of the semaphore, while the state of the mutex is modified only by the process that may request or release a resources. If they want to release some resources, so the lock will be released. If they want to require some resources and if the shared resource is available, so the lock will be provided to the thread or the process. Resource management: if no resources are free, then the process requires a resource that should execute wait operation. If there is no resources available, and if some thread or process wants to acquire some resources, then they must wait for the resources. It should wait until the count of the semaphore is greater than 0. If the count becomes greater than 0 in case of the counting semaphore, or it become 1 in case of the binary semaphore. In case of the mutex, if it is locked, the process has to wait. So if it is locked, the process has to wait, and here if no resource is available, the process has to wait. The process should be kept in a queue. This need to be accessed only when the mutex is unlocked. You cannot you cannot have access to the mutex if it is locked. You can have multiple program threads and you can have multiple program text and mutex, but not simultaneously. Semaphore can have simultaneous threads and they can switch between threads, but mutex can only have one thread at a time. Value can be changed by any process releasing or obtaining the resources. Any process who requests to get the resource or acquire the resource can change the ownership, but only the object which have lock on some shared resources will have the authority to change or to obtain the lock or to release the lock. Only that one process can change the status of the mutex. But here, any process which needs some resources and the resources available can change the state of the semaphore. They have types. Semaphore have type, binary and counting, but mutex has no subtype. Semaphore value is modified using wait and signal function or method. Mutex object is locked or unlocked. Resource occupancy: it is occupied if all resources are being used and the process requesting for resources perform wait operation and block itself until semaphore count become greater than 0. If the count becomes greater than 0, so the resource cannot be occupied. In case if the object is already locked by some process and the new process requesting resources, they have to wait and should be put in the queue by the system before the lock can be released by the owner process. So we have finished the material of the today lecture, and just only the last slide which explain some. Okay, in the last slide we are going to discuss a special type of lock, which is spin lock. So now let's see what is spin lock. Spin lock is a special type of lock, and it can be used in the situation if some forces want to enter the critical section. It must loop continuously uh, and waiting for a call to acquire a lock. This is a spin lock spins while waiting for a lock to be available. So what are the advantages of the spin lock? No context switch is required for a process waiting on a lock. Good for the system where it's known that lock are for short time. So if the lock is for short time, so spin lock are better in that situation. It can be applied in multi-process system where one thread can spin on one processor while another thread processes its critical section in another processor. So that was some special type of lock called spin lock. I think it's enough for today, and I expect you to run all the program shown here. So best of luck and see you in the next lecture.